All right, let's try this one out. We're going to jump into this example with an impulse happening here. And in this case, we have a moving object that hits here. So when they collide, that's where the impulse is going to happen, right? The wall is going to impart some force onto the ball and cause it to recoil. So we can see we've got these different angles coming in, going out, different speeds going in and out. We're going to neglect the ball's weight. And the reason for that is kind of interesting. The force that it hits it back with, if you want to think of it that way, is going to usually be so much greater in magnitude that something like its weight acting during the amount of time of the collision is going to be almost non-significant, right? As as it collides, right? The fact that it has its own weight pushing down during that fraction of a second, that weight times that time provides a very small amount of impulse compared to the impulse that bounces it back. So we're going to neglect the ball's weight during that impact time. And they want us to find the impulsive force exerted on the ball. All right. So we could draw up some diagrams and then apply our equations that we came up with momentum and impulse to come up with that force. So here's what we have. This is kind of a useful way to think of it as we've got a right before impact, we've got a right at impact, and then we've got a right after impact. Right, so this is during the collision here. So we come in at the 45, we've got an mv1, velocity 1. Then we've got a force times time that acts on it. And then we've got, at that same time, we could say we've got other forces acting during that period of time. But like we said, the weight times time, that's going to be such a small impulse compared to this force times time. So we'll just leave that out. And same with the normal force, that's going to be relatively small compared to this force times time of the actual impulse that will make it bounce back up. So that's during the impulse, so you can get rid of these two. Really, it's just the force times time equals the mass times velocity to our final momentum. So it's changed our velocity and it's changed our direction at that point. So what's our force going to be to change it from here to there? Well, we can plug what we know into our equation and solve for that middle term. Right? So if we say we've got a mass of 0.5 kilograms, yep, that's where we're getting that 0.5 there, times the velocity was 25 meters per second. So we could plug that in, cosine 45i, and negative is going down and to the right, right? 25 sine 45j. That's our velocity incoming. Then we have this unknown impulse term that we're solving for. And we are going to end up with a final mass times velocity, which would be mass again of 0.5. And the velocity that they gave us was 30 degrees from the horizontal. So we've got cosine 30 in the I direction and sine 30 in the J direction. So that is our equation with everything plugged in that we know. And we can solve it for this impulse term, force times time. Sometimes they give it an I in the book, but yeah, it's just that force times time. And we'll end up finding in the I this much and in the J that much with some interesting units, Newton seconds, right? Force times time. That's why it's like that. And if you wanted to get a magnitude, you could do like we've always done Pythagorean theorem. We got 12.2 Newton seconds. Now, that on its own is almost useful. And what we'll see with the majority of these next examples is they would say something like, okay, maybe that is a 6 Newton force. How many seconds should it act for to cause that change in velocity, right? Or they could say that is occurring over 0.25 seconds. Therefore, how much force did it impart? And so we could take that I right? That force times time term. We could divide it by the time, and that would give us an average impulse force. Or we could divide it by the force and we could end up with the time, right? And that's how most of these will go for the rest of it here.